Have you ever marveled at how some software applications can process vast amounts of data in the blink of an eye, while others struggle with much smaller tasks, leaving you waiting? The secret often lies in the efficiency of their underlying algorithms. Optimizing an algorithm's time complexity primarily involves three core strategies: fundamentally changing the algorithmic paradigm, selecting and utilizing appropriate data structures, and carefully reducing constant factors within the implementation. Each approach targets different aspects of how an algorithm consumes processing time. The why behind these strategies is deeply rooted in computational theory, specifically Big O notation. This mathematical notation describes the limiting behavior of a function when the argument tends towards a particular value or infinity. It allows us to categorize algorithms by how their runtime or space requirements grow as the input size increases. For instance, an algorithm with an O of n squared complexity will become significantly slower than one with O of n logarithmic n as the input grows, because the number of operations scales much more rapidly. By choosing a different algorithmic paradigm, such as moving from a brute force approach to a divide and conquer strategy, we can often achieve a vastly superior Big O complexity, leading to exponential performance gains for large datasets. To effectively apply these optimization strategies, start by profiling your current algorithm to identify the genuine bottlenecks, rather than guessing. Once identified, consider if a different algorithmic paradigm, like dynamic programming for overlapping subproblems or greedy algorithms for optimal substructure, could offer a better Big O characteristic. Then, examine your data structures. Replacing an inefficient data structure, such as a linked list for frequent random access, when an array or hash map would be faster, can yield significant improvements. Finally, optimize the inner loops and critical sections of your code by reducing redundant computations and making operations as lean as possible, which targets those important constant factors. An interesting detail here is the concept of amortized analysis, which provides an average performance guarantee per operation over a sequence of operations, even if some individual operations are expensive. Understanding this can inform choices for dynamic data structures like dynamic arrays or hash tables. Another key insight is that while Big O determines scalability, the constant factors, often overlooked, can dominate performance for smaller input sizes, meaning even an O of n squared algorithm might outperform an O of n logarithmic n1 if the constants of the latter are very high. By systematically analyzing an algorithm's Big O complexity, making informed data structure choices, and meticulously refining implementation details, you gain the power to transform sluggish processes into lightning-fast operations. This approach not only boosts performance but also enhances the overall user experience and scalability of your software systems, ensuring they remain as efficient and responsive regardless of the task at hand.
If this helps you fix faster, like, subscribe, and keep debugging with us.